Today we're going to continue our journey into the world of classical computer vision. We're going to have a seminar on object detection with yet another method of detecting objects. Today we're going to talk about contour analysis, contour obtainment, contour processing, visualization, simplification, and so on. The problem that we're going to solve is to detect these rails. These rails are made of wood and they're placed on a concrete floor. So one of the ways to detect them is to obtain their mask by color. But as we discussed previously, there are certain difficulties with that in varying lighting conditions. And if we will have just different material here for the concrete or for the rails themselves, it will result in certain problems. So we'll try something different. We will try, along with the contour analysis, we will try adaptive thresholding methods. The contours are needed here to detect the corners of these rails. They will be distinct from each other and we will detect them separately. We will not detect this little bar over here, or it's better to say that we will delete it. So let's begin this seminar. I have copied the contents of the previous seminars and they are in the same Jupyter notebook and it's becoming longer and longer, but it's just for the sake of simplicity. I will copy certain parts like connected components analysis, maybe something else. In the end of the part of the course that is about classical vision, this notebook will be pretty lengthy. And also today we are going to use an alternative method of visualizing images. Previously we have used OpenCV library, and now we're going to use Matplotlib. So I will import all the necessary libraries. And I'm going to load the image. Let us try to visualize this with Matplotlib. Okay, it's kind of working. Let me increase the font size, by the way. Do you see something suspicious, conspicuous? What is the difference between this image and this image, apart from the size? The difference is that this one is in the shade of blue, and this one is in the colors of the real wood. So the reason behind this is that in OpenCV library and in Matplotlib library, different color spaces are used. Not that much different. One is RGB and another is BGR, but we have to remember that and keep that in mind. So if we want to visualize this image as we are used to, we have to exchange the colors, exchange the color channels in this image. We can do that either by manually exchanging the channels or by using a conversion function from OpenCV. The function that is already familiar to us. And it's along with some distinct and different color spaces like HSV, YCBCR, lab. It also supports this almost trivial color conversion. RGB to BGR. Let's run it once again. What? Okay. Yep. So now the color space here is the right one, I mean the one that we are used to, it doesn't make much of a difference, but still. I mean, in terms of the detection, it's not important, the order of the channels, but for us, it's better to look at objects in RGB. So the next thing that I'm going to perform is I'm going to do the adaptive thresholding. Let us check the documentation of OpenCV. And here are some examples of different thresholding methods. Threshold is like a half of in range. That's pretty much it. We are setting up a value that divides all the pixels in the image into the group with the less or equal values and greater values. So as a result, we get a mask. And the problem with such an approach is given as an example here. So someone is trying to apply a threshold in order to detect the numbers. And it's not possible with one global threshold because of the varying lighting conditions on the different parts of the image. And here the adaptive thresholding comes and saves us. What does this adaptiveness essentially mean? The adaptiveness here is in the process of calculating the local threshold or the surrounding of each pixel. Basically, we're calculating the average in a certain window around the pixel, and then we're comparing the value of the pixel to this value. If this difference between them is greater than a parameter of the adaptive thresholding, we consider this pixel to be outstanding enough from the global average, from the local average. That's the idea. And there are two options here. Here we have adaptive mean thresholding and adaptive Gaussian thresholding. The difference between them is the weights with which the pixels are averaged in this surrounding, in this window. In mean thresholding, as you can tell, all the weights of the pixels in the window are the same. And in adaptive Gaussian thresholding, they are weighted in accordance with the Gaussian distribution, the Bell, basically. Here you can see that in this case, for this picture, it gives better results. And just once again, this local thresholding or adaptive thresholding has two parameters. First of them is the size of the window for local mean calculation. And the second is the offset between the mean and the pixel that is necessary to consider a pixel an outstanding one or bright enough one. Another method is called Otzo's binarization, and it works as given here. So let's suppose that we have a bimodal distribution, that it has one maximum and another maximum. And in between of them, we don't have that much of pixels. You see this bimodal distribution in the image. So the one global maximum is the concrete, and the smaller one is the rails themselves. So here we're going to use Otzo's binarization. And the idea of this method is to find out a threshold somewhere in between so that those classes are separated in the best possible way in terms of the inner class variance. And here are the formulas. You can check them in the documentation. And we're going to use this method. Let's copy this. This line. Well, for now, let's comment that out. The problem, or not the problem, but the thing that we need to consider here is that the input for the thresholding function is a single channel image. And by now, our picture is a 3-channel array. So we have to do something to it. We can probably bring this whole image to the grayscale. We will try it. But it seems like this is not the best way to do it. So we're going to consider one more method. But first, let us try to transform this image into gray. RGB to gray. And we're going to visualize it. If we do it like this, the image will be overwritten. And this is why I have to use this imshow. Oh, no, not imshow, excuse me, just the plt.show function after the first imshow. So here we can visualize 2 images. Maybe you're curious about the color scheme in this image. Why is it like this? The answer to this question is that the default color scheme that Matplotlib uses is from blue to red through green and yellow. So this is basically the one. And we can change this color scheme. As far as I remember, it is called CMap, like this. Yes. Okay, so now we have these images in shades of gray. And that is, I could say, more convenient. Well, let's try applying this thresholding. In the example, it's without 2 in the name of the library. And I will do some nice spacing. Okay. What's a binarization? And it will be a mask already, so we don't need to change the color scheme. Okay. So, is it good enough? I think it is. But just to cover this whole topic, let us try another one. We can use one of the channels from HSV color space. So the idea is to get some single channel representation of the original image that is capable of representing the differences between the concrete and the wood in the frame. So let us take a look at this image, and we will compare it to, basically we will visualize all the channels in the HSV color space, and then we will choose the best one. So let me change the color space here to be to HSV. Yep. It will be the first channel of HSV, and the same for those 2. Second channel, well, third channel, first channel, channel number 1. Okay, so this is the original image. This is just the grayscale. This is the hue channel. Does it make much sense? Well, we can try. And this is the saturation channel. Concrete is not that much saturated. And it seems like all those channels give good enough results. Well, I mean, you can tell which one, for different pixels, you can tell which one is a part of the rail or not. On the other hand, here we can see that the shape of the rail is really missing. So it's somewhere here, but these areas, they are not representative of the shape of the rail. So I think we can skip it. We can skip the hue channel, the color tone. It's a bit noisy. So I will comment out this one. And here I'm going to add a couple more of adaptive thresholdings. And this value, this return or result, is the threshold that was chosen after this whole procedure of classes separation. So grayscale, also saturation, also value, also. And now we're going to visualize the results of these binarizations. It's more or less a matter of experiment. So let us check which one is working best. Original image. This is the grayscale. Saturation, value. You can see that saturation and value, oh, no. The grayscale and the value are pretty much similar to each other, right? That's because the grayscale image is obtained by adding together weighted channels, red, green, and blue channels. And here we have 3 different versions of binarized image. Here it's a version from the grayscale image, here from the value from HSV, and here is the version from saturation. And in my opinion, this is the best one by far. So we're going to work with this one. We'll comment the rest. And I will run this code once again. So just a quick recap. What do we have here? First, we have loaded the image. We have transformed this image. We have changed the color space to RGB from BGR. After that, we have converted this image to HSV color space. And we have applied adaptive auto thresholding to the second channel of HSV color space, or more specifically, the saturation channel. As a result of this auto binarization, we have obtained this mask, and it seems to be a good representation of the shape of the rails. That's it for this part of the seminar. We will continue exactly from this spot later. Let us continue with the seminar. Here we're trying to get the contours of these rails, by trying to detect them. And the way we are doing it is the adaptive thresholding that we have applied to the S channel, or the saturation channel of the HC representation of the image. So the next thing that we are going to do is we are going to try to get rid of some of these darker areas inside of the mask, and probably we can try to make this thing smoother. So what we can do is we can apply a blurring before the color space conversion. So I will do it here. And for this operation, we, as usual, have a function in OpenCV. Let us do it with, let's do it with a small blurring kernel, and we will try to spot the difference. So probably the image has to be visualized before the blurred version. Image, blurred, channel, binarization. Okay, let's see. So, is there any visible difference, or not that much? Not that much. First of all, because the images are quite small, but probably we can increase the size of the kernel, and the difference will be more apparent. Or we can increase it even more. That would be 7 and 7. Yep, so now it's blurred just a bit, and these areas over here, these lines and borders are not so sharp. Well, it didn't help out with the darker areas over here, but probably the contours are smoother. So it's up to you if you want to use it or not. Let's compare it with the blurring one by one, which means an identity, just doing nothing. Well, here we have got rid of a line of black pixels that was going inside the area of the mask. So probably it's better with some kind of blurring. And from this point, we are going to work with this mask. Okay. The next thing that we are going to do is we are going to apply contour analysis. What is basically a contour? A contour is a sequence of points that encloses the object that we're working with. They could be simplified as on the right, just the corners, or not simplified as here. And we're going to use this function, CV2, find contours. So the first parameter of this function is the image, then the mode of the contour obtainment, and these modes could be retrieving only the external contours or getting them in a form of a tree so that the contour that is inside another contour could be traced to belong to it. So we're going to use the simplest way possible, we are going to extract only the outer contours because we are basically interested in precisely them. We're interested in this contour. So we're going to use this function. And how many parameters does it return? 3. Okay, I hope that this documentation is up to date. We really need only the contours here. I'm missing something. Okay. Now I'm checking the examples, and that's more than an encouraged thing to do. So, yeah, we have to add this parameter. And let's check what's going on. This is the contour approximation method, and we are not going to perform any approximation on this stage. We are going to perform approximation later. And for now, it's enough for us. Okay, contours. Let's check the usage example. Contours and hierarchy. Okay, so in this version of OpenCV, it has 2 output values, and the first of them is of our interest, and the second, the hierarchy, we can ignore because we are retrieving only the external contours, so they don't have any hierarchy here. Okay, let's print those contours. So there are a lot of them, right? Or not? Or it's the same contour that is long? No, there are many of them. And let's try. Let's try printing the length of this array of contours. There are 12 contours in this image. Or not in this, but it's better to say here. So the next thing that we're going to do is we're going to visualize them. And in order to do that, we can use this function, draw contours. I'm going to do it in the next cell, and it will work just fine because of the precious properties of Jupyter Notebook. So this means that we're visualizing all the contours. This is the thickness of the dots. This is the colors will be green. And the only thing that we need to do is we have to pass this image to the output. Yeah, so here are the contours, and you can see that there are indeed a lot of them. The biggest one is over here, and there are some smaller ones, or those are only the parts of the contour. I'm not precisely sure, but for sure we can tell that here is a contour, here's a small contour, and here are some small contours as well. And the next thing that we're going to do is we are going to filter these contours out. So we don't need the shortest ones, the small ones. They belong to these small objects that we're not interested in. So I will move this code upwards. Why I'm going to do that? Because it will be more convenient. I'm drawing on top of this image, and it is altered now, so it is changed. If I'm going to run this code again, it will give us a different result. Does it? No? How come? Excuse me, yes. This code is loading the image from scratch, and if I'm going to visualize this image over here, it will be with those green contours being drawn. So you have to keep an eye on that in order not to be confused. Okay, I will draw the contours here, and I'm going to get rid of this printing. And I'm going to clear this code just a bit. Okay, so let us go through these contours, all 12 of them, and check their length for a contour in contours. We're going to print. I believe this is the function that does it. Okay, so let's print the lengths of the contour. No. Closed. True, right? Yeah. So the difference between those two ways of, oops, my bad. The difference between two ways of calculating the length of the contour is that we can include the last part of it between the first point and the last point. We can include it in the length, or we can omit it altogether. The contour is a thing that, well, the sequence of points basically, and it could be closed, two connected, so to say, or open, like a chain. So here I'm passing true as a parameter, and we're going to see the lengths of the closed contours. So let's see, there are lots and lots of small contours. This is the length in pixels, and the big one that we're probably interested in is this one. So let's leave among the contours only this one. Filtered will be an empty list, and if a length of a certain contour is greater than, say, 1000, we're going to add it to the filtered list. This is the one contour. So we're pretty much happy with how is it going. We have filtered out all the unnecessary parts, and now we only have to get rid of this bar over here because I promised so. This bar, this item, is a thing that is keeping the rails together. It's keeping them on the proper distance from each other. And these whole rails are made for a land-based robot with wheels, and it's the robot is supposed to park on these rails, but without going too much into the detail, we can just say that the robot is more interested in the positions of the rails themselves, not in the position of this bar. So we're going to get rid of the bar. And we can do it before the contour analysis. We can do it with morphology. How are we going to do that? Well, let's take a closer look at this mask. We can try to get rid of this bar with morphological opening. So at first we can do erosion. We will get rid of this bar and these dots as well. But the problem here is that along with those desirable outcomes, we will destroy the shape of this part of the rail. So at first, let's do the morphological closing, and we'll get rid of these black holes here, and after that we can do the opening with a bigger kernel size. So let's comment a couple of unnecessary things here. We have already seen them enough. And for now that's fine. So we have a mask that comes from the auto-binarization of the saturation channel in HSV color space. And the next thing that we're going to do is we are going to apply morphological closing. The first parameter is the input, the second parameter is the operation that we're going to apply, morph, close. And the last one is the kernel. And the kernel will be with ones 5 by 5. I will name it closing kernel, in contrast to the opening kernel that will be bigger and that we are going to create later. So it's going to be an NumPy array of ones with the size 5 by 5. Maybe we'll increase it. Let's see. The type of the data is as usual. And here I'm going to do some copy pasting. Yes, that's fine. So let's first visualize the result of the closing. Remember that I have to move this downwards. I wanted to say that remember that we are passing the original mask to the contour obtainment, but yeah, we even have to get it to the place after the morphology. Okay, so Let's see. It has helped us with some of the black holes over here. And the only thing that is needed, we only have to increase the size of the, the size of the kernel. Let it be bigger, let it be 9 by 9. Yeah, that's fine. So now we are ready for the morphological opening. We can do almost the same thing. The only difference is that the kernel will be much bigger, like this. The operation will be morphological opening, and it will be opening kernel. And the input here will be the result of the closing. Closed, okay. Not really. So the kernel should be much greater than this. Maybe 29. Let's see. Nope. 39. Kinda. Almost there. Maybe 45 will do the work. Yeah. That's pretty much fine. And the only thing that we need to do is we need to pass the output of the morphological opening to the contour obtainment. Yep. So finally, we have the contours of these rails separately. They do not follow the precise contour of the rail in the image, that's for sure. Here, we have some artifacts. Here, the corner is not that visible. But these errors in the positioning are more or less acceptable, I should say. The contour is clearly in place, so this is fine. For a small demo of 49 lines, it's okay. And this completes the part of the seminar that was about the contour processing. Oh, no, not exactly. Excuse me. So that's a semi-final, okay? What we have done? We have obtained the mask, we have processed this mask, we have separated the rails, we have got here, and we have those contours. But they are too much, they have too much details, right? They follow each small curvature of the rail. The last thing that we're going to do is we're going to loop through these contours, or we can even do it here. If we're interested in a certain contour, we can use its length to simplify it. Let me show you. So we have this kind of a contour that follows all the curvatures and all the parts of the mask precisely. And we're going to use this operation called simplification in order to get this type of a contour that follows the general structure of the area of the mask, ignoring the tiny details. How are we going to do that? we're going to use the function by the name of approx polydp. And its input is, well, yeah, here we even have a pretty visualization. So its input will be the contour, and the precision or the length that could be neglected while calculating the approximation. So we're going to get rid of tiny details. We're going to get rid of those points that could be removed without the whole contour changing too much. So let us use this function. First, we will need the length. And if this contour is of our interest, if it's big enough, we are going to calculate its approximation. Filter.append to prox, and the approx variable will be the output of the function approx polydp. Here we have to pass a contour and the length multiplied by some small constant like this, let's say 5%. So we're going to neglect the details or the points that could be removed without the contour moving to the 500th of its length. The bigger the contour, the bigger details could be neglected. That's the logic here. And didn't I forget anything of the parameters? Let me just briefly check. You have to check the OpenCV documentation by image search and Stack Overflow as much as possible. Okay, so let's find the documentation page. Yes, here. And the third argument specifies whether the curve is closed or not. We need the closed form of the contour. So I'm going to pass through here. Let's run this. Seems like we have overshooted, and the contour is simplified too much. We don't need that. We don't need all the contours to come to a form of just triangles. It's better to have not rectangles, but the contours with 4 points. That's closer. So if we want our contour to follow the shape of the area of the mask more precisely or closely, we can increase the number of the points here. But in order to park the robot to the rails, it's pretty much enough to do it like this. So finalizing everything connected with the contours, we can do the following things. At first, we have to obtain a mask and process it so that proper contours could be extracted. Then we can obtain the contours themselves, and they are going to be represented as sequences of points, or ordered sets of points. We can visualize these contours, and we can filter these contours by their properties, by their length or by their area. We have not done that. but you can do it on your own. You can Google OpenCV contour area, and there will be a function that is capable of calculating the area that is inside of the contour. And the last thing that we can do with the contours, we can simplify them in order to get the rough but robust, short, simple representation of the contour of the object. That's it for this seminar.